So yeah, now I'm recording again. So as I was saying, the objective for today is that we review some publications and some major ideas in general. So on recurrent neural networks in that. So now in the class you have seen what is more or less a recurrent neural network about, but there are major open topics up to this date. As you have maybe heard, recurrent neural networks have this reputation that are harder to train than, for example, CNNs. This is one thing. The other thing is also that there are discussions asking, do we actually need a recurrent neural network? So by now there are architectures that can do similar things to an RNN or an LSTM, but they do not need, they do not have some of the problems that this recurrency brings. So can we just use them instead of using RNN and so on? And in general, so what is like the things that are out there and how RNNs work from scratch and so on. So this will be like topics that we'll be seeing this week and next week. So basically trying to compare the general landscape and understanding so in depth how do they work and so on. So the first thing that we'll do is we'll check one of the first surveys that will appear in literature back in 2015. So it's already some years, but still is one of the most relevant ones on recurrency. And the idea behind, so this survey is first to explain, so why do we need actually recurrent neural networks and in general this type of architectures? And of course we know that this, let's say, for sequences. And as we have seen in the class, there are multiple types of ideas of sequences, right? So it can be, for example, so video sequences, but we also saw that even a set of emojis can be considered as a sequence, right? So here we see that the use cases for recurrent neural networks are very varied. So for example, in this case, it could be also for image captioning. So also for generation of text. That is not one of the major focus of this class, but of course it's a classic example. But the challenge behind is that although we always think, okay, we are working towards very advanced architectures, in fact, these architectures are in the end relatively simple, which is not a bad thing, but maybe more worrisome is that they're fragile. Yeah? So here in the end, we want to select robots, but we end up with basic classifiers, to say. And the question is, what it is that did went wrong? Is that on one side, most of the ideas that exist, so for how to work with the data, it starts from being so for tabular data, right? So the data that we have in businesses, data we have, let's say, like in our computers for the most part, it tends to be so tabular, and a time series, a sequence, and so on is not like that, right? So on one side here already we see a challenge in that how we're working in practice compared to how what it is that we have as models. There's here a disconnect, right? So we need to model it. And then there are other challenges as well. So the challenge here is, of course, on how do we incorporate so variable length of the sequences. And as we know, most problems have the situation where, let's say, we have a web shop of users, and then this web shop measures the sales of for each user. And of course, people come to the store at different moments in time, right? So some people might have joined the store in October of this year, others in summer, and others like in spring. And that means that we'll have sequences that are of different lengths, because for some sequences we'll have only 3 months of observations, whereas for others we'll have 6 months. But then when we want to train our models, is the question, how do we do it with those different sequences? How can we consider that they will not have the same length? One of the most easiest approaches is that we can say, okay, we'll have a sliding window where we do not consider the full length of all sequences, but rather we are moving our window. That way we will only consider a subset at any given time. And that way we can handle these sequences that are not of the same size, right? Then another challenge is that, so what do we do when for models that actually they were not made for sequences. If we think about it, and you know, for example, for your machine learning class and so on, if we think about, say, let's say like CNNs, and so as a classifier, so they work very naturally for images. But if we want, for example, to use them for sequences, and in this case, let's say, for example, for text, this is less suitable. And why is that? Is that on one side, traditionally, most models assume that we have a fixed size input and a fixed size output. But we're already seeing that if the input might not be necessarily of the same size, so when it's fixed, it might so change, and also it might be growing. So if we think about all this idea of the store and the users in our store, over time we'll have more purchases from those users, and then as a result, the input that we'll be having in the model will be getting larger and larger, right? And the other thing that it is connected to that, and is very common in time series, in sentences and so on, is that there is some connection in between the multiple sequences. So if it is a time series, you can think about so that, and we say in this example of the store, you might think that so certain users, they belong to, let's say, similar segments, and then their behavior might be connected. So how can you share this information across the model? How can you do it? So already here we see that on one side, these traditional models that already existed had some problems for the data that we're using, but also more specifically for this type of so sequential data that we are having now in this course or in general, right? So there are so many cases where we're working with sequential data, and if we say, okay, let's try to use just a class of CNN out of the box, we will not be able to use it. Of course, as we'll be seeing next week, there are many architectures that are building upon CNNs, and in fact, we might discuss today one of them. And it is possible with modifications, but out of the box, we have these limitations. Then it's a question of so what people did in the beginning to limit this, and we must be thinking that most of the ideas that we're seeing for neural methods for sequential data, they come from the NLP community, and as a result, especially if you look at earlier material that appeared, let's say 5, 7, 8 years ago, pretty much everything is first and foremost for sentences, and second, it will be for so time series or let's say event sequences and so on. So what people said, okay, how can we handle this idea of that we need a fixed size input, but sentences or sequences that are not fixed size? The very first thing was to work with bags of words, and maybe you might be seen this if you have taken the NLP class, or in general, if you have worked a little bit with text, but intuitively it's just that instead of trying to work with the sequence itself, is that we convert this, and then what we're doing is we're saying, okay, let us count how we have a vocabulary. So in this case, let's say like a dictionary, but if we're talking about other type of sequences, let's like emojis, the emojis that all the emojis that exist in the world. So we set this as our vocabulary, and then we start counting how many times each of those emojis or each of those words appear in the given sentence or the given sequence that we're working with. So what happens is that we lose the word order, and but as a result, the benefit is that we can have now a vector fixed sized. And there are, of course, problems with this. If we think about so sequencing, that the core idea of sequence is that order is important, and we cannot just break it somehow. And here's, for example, this example that if we break the order, then we have for example, sentence that says scientist exterminated by raging virus. And then we can also have virus exterminated by raging scientist, which are obviously completely different sentences with very different meanings, but for a bag of words, it will not be possible to recognize it. Now, if we think about how we have brought we have bridged this gap is that, of course, we try to build embeddings of fixed size, and also we will see in our seminar how in the end a RNN and even a transformers is nothing else than just, let's say, like more advanced versions of one-hot encoding, right? So there is so much mystery and people imagine so much behind these architectures. In the end, they are not. They are just, let's say, intuitive next steps from working with one-hot encoding for data, and starting from exactly this idea of we have inputs that have different lengths, but we want actually to fix them somehow while preserving on one side this order, but also trying to have as much information as possible from it. In NLP, of course, there are ideas of from word to peg, globe, and so on. And then what can be other ideas that we can consider? Well, we can think about something such as Markov chains. If we think about the literature before, how we had it with neural networks, and we want to model sequences, we could have used Markov chains as a possible architecture to work with sequences. And they were very popular for text-related tasks, but also for main tasks connected to time series and so on. So they were very well used and understood. And there is a lot of literature behind. And up to this date, so you can still use them. But how is it that now, if you look at the latest publications in the literature, you do not really see them being discussed, and they're still being used, of course, but they have a little bit more or less disappeared, even though 10 years ago they were all the rage in the literature. Well, there are some limitations on working with the Markov chains. On one side, we have to infer this number of hidden states, and this is basically something that's quadratic. And if we look at how Markov chains work, in that we have these inputs, and then we're passing it across different states. In fact, they are very close to a recurrent neural network, but with the difference that RNNs can have many more states, many more hidden states, but with the benefit that the computation is only quadratic. So on one side, we can so represent more, but this will not grow on the same way that it will be with the Markov chain. And this means that this is very suited for longer data. This is another thing that we'll be seeing. So if we think about what motivates the whole research behind sequences, one is this idea of I have variable input, but I want to fix it. And the other one is this variable input, it can be as large as we want. It can be very long. And we want to make use of these very long inputs. And for most architectures, and of course, for the traditional techniques such as Markov chains, there's a limitation that a very old input in our sequence, and if we're talking about, let's say, like a time series, very observation points that are in the past, they will not be considered by the architecture in RNNs, Markov chains, and so on, LSTMs. So that's why we have transformers. You see, like the second point that motivates the whole research field in sequential data, how we can make use of historic information for sequences that have a very large length. And if we see here in this screenshot that we have here, so magnify it, is that from the simple idea of RNNs, by now there has been multiple ways how we can do the architectures. And probably you saw this today with Alexei, where we can have, of course, let's say like the classic one is that so we have inputs, and then we have some hidden states and so on, and then we have like one single output. But then, of course, depending on what we're doing, we can change this setup and then have single inputs, but then multiple outputs. So this is, for example, a very common task in like an image captioning, but also you can think about other ideas in let's say you're thinking about so time series forecasting. that, so you say, okay, I want like the next 10 steps ahead. Then you will have one single input, let's say like one sequence, but then you will have multiple outputs. Or for example, if you're saying for some type of probabilistic forecasting, so that where you will not be inputting just one single observation, but you want to have a distribution, then here you might be thinking of something such as this one-to-many architecture. But then there is other ideas of the opposite, a many-to-one, in that if we're working with sentiment analysis and then we're having all this type of different sentences, but then in the end we just want, we're just classifying them, right? So we just want to say, okay, these are like positive sentences or these are negative ones, then there will be many-to-one. And then if we think about situations such as in video captioning and so on, but also we think in the topic of time series, we can have multiple sequences. So let's say a data set that has so different sequences for the same user. For example, we can think about smartwatches. Smartwatches are collecting from us the number of steps that we're making, our heartbeat, and also the speed at which we're moving over time. Yeah, so that means that all this can be as an input, and then the same model can be used, given that this for the same user, it can be outputting for each of these sequences individual results. And in this type of architecture, we can have these two variations. One is that at each step will be outputting something, but it can be others where first there is like some input, and then so we want to predict ahead in time, and then only later we'll have like the output. So here again, it depends if we want, for example, to make use of time. So in this many-to-many, like the one here on the left, or time is not that relevant, and it will be at the same moment in time, for example, for generative text models and so on. Yeah, so then so far so clear. So then we have here a situation of, on one side, historically we see we have this fixed input. We want fixed input, but we don't have it. And the classical models, they were made for other type of data, let's say like images or just general observations. So potentially tabular. But the models, the data that we have with sequences is not like that. And also, of course, we have the situation of we have something that it should have a rather mild computational time, right? So what can we do there? Well, then people thought, okay, why not so having here neural networks? And here, for those who forgot already what we learned about in the machine learning class, so the general idea is that we have these different layers, and we are passing the different information across different layers using activation functions, right? So that so here we have so this sigmoid, and then we see that in the end, the only thing that we're doing is that we have our inputs, and so with a matrix of weights. And this is basically what we'll be having for the activation function, that this activation function that in this case we have here sigmoid, we can be so hypertangent, ReLU, or there are many others. We can just use them in order to decide if this input is relevant enough to pass it to the significant to the next so stage. So here in this case, we just have so here one layer, and of course we know this idea that is inspired by the neurons and so on, and yeah, and then once we have this, then what we want to do is we want to use backpropagation, right? So in that, so we want to know what would be this rate of change in the loss function for each parameters. So that means that first, we pass all our input so through the activation functions in hidden layers, and we obtain an output, a prediction. But then what we want to do is we want to use backpropagation to basically assess, and for this we'll be calculating the algorithm. So we'll be doing a backward pass. So here, what we want is we want to assess basically, is this a prediction? Is this prediction relevant? And if not, then how can we adjust our weights of our matrix of weights in order to approximate as close as possible for the actual result, right? So this is basically the very classic one layer so network. And then it's a question, okay, how does a RNN differ, right? And the idea of the RNN is, if we see it looks very similar to how it will be for just a flow forward neural network, for a very classic neural network. But the difference will be in what happens in hidden layer, where you can see here this magenta arrows. So basically what it says is that we are sharing so the results across the states. And here is how it will be classically represented in, let's say, in how it will be aggregated. But if we unfold it, then we can see how it is across time, right? So that here we have a layer, and we have one input at so the first point in time. And then for the second point in time, what happens is that not only we're passing our input, our raw input, but also we are sharing the results from the hidden layer that were coming from the first input, right? So here, this means that we can pass the information from the previous point in time. But otherwise, if we look at it, we are using basically the same activation function as we had. So here we can see that here we have also a sigmoid, and then we have what we're doing is we're aggregating the one that was for the first point in time, and then for the second point in time, and then we're having here so we're adding here a bias, and then using softmax in the case of for this output. So here what we're seeing is basically they are nothing else, or they look basically almost the same as a historic neural network architecture. However, if you look at the difference, it's just slightly. There is the minor difference, which is let us start sharing the information across the different hidden layers by form of, so here summation. And then here you can see that so for training them, as we're unfolding them, is just this feed-forward neural network with this weight that is across the different time steps. And now we just call it backpropagation, but and we do not differentiate between backpropagation for these classic architectures, and we say backpropagation applies also for these ones here. But when it came out, basically 30 years ago, it was called backpropagation through time. So also, especially if you look at older literature, if you you will still see that people say, oh, and we train it using this BPTT, backpropagation through time. But now these days, people just say backpropagation, and they do not make this difference between so working with the one that is for traditional neural networks and this one that is for recurrent ones. And then within this same idea of backpropagation through time, there are also it appeared different modifications, right? So then this one was so to cut errors after some number of steps that they call truncated backpropagation through time. So it came out pretty much at the same time. And this is, let's say, like how people started training so neural networks. And also that here, what you see is that although, let's say, this is something that we use today and we consider modern, in fact, already in the early 90s, they were using RNNs. So they are very historic, and there's a lot in literature. There's also like another word of caution whenever you're looking into literature from RNNs, Lstms, and so on, in that if the vocabulary, how people represent and how they explain these architectures has evolved through time. So if you go and look so at these very old publications, you might have some challenges understanding them because how they were explaining concepts and also how they were describing how these neural networks work is rather different as how people do it now. And the RNNs are not the only ones that appear in the literature and that you will be seeing. There are other approaches. So also for here sequential data and using neural networks. One of these is so here this Hopfield network. And here the idea is that you're seeing that there is some sharing across the different so the different states, and this can be something similar. That's what we have for the RNN. And one of the things that is here is that so they were not using back propagation, and we can here so basically let it run for some time, so to update the rules and so on. So they are still used. In fact, recently there was last year there was a publication that was very well received called "How Fields All You Need," and where they revisited some of these ideas. However, if we look at in general for sequence, working with sequences and so on, they are not common, or really nobody's using them. So you will not see anyone, let's say, trying to benchmark Hopfield networks against RNNs, or sometimes it's forecasting task. That doesn't happen. And there are here also the Jordan networks, and so how as you see them is that they look similar to the RNNs in that on one side we can see how there's here magnified. So we are having the different having our hidden layers and our input. We're seeing here that there's here some differences in that in the classic RNN, the input goes to each of the hidden layers. Here we're seeing that the full sequence basically goes to each of the hidden layers. But also we're seeing that the output, we're passing it to these context units. And this is something that the RNNs do not have. And we also, of course, have the recurrency. The recurrency that happens not only for the context units, but also for these hidden layers here last year. So here we see some similarities, and you can still see them. But here, this is something that by now, let's say, other approaches have superseded them. And if we look at the different architectures that we have, so here, they more or less resemble to like a many-to-many RNN. Yes. So of course there are here some differences, but let's say that yeah, so they do not justify. And then there is also the Elman networks, and so if you see here, the Elman networks are very close to the RNNs, with the difference that here the output is used by the hidden layers, and it is rather the hidden layers that are being shared with these context units, whereas in the Jordan nets is this output that goes from the hidden layer that goes into the context units. So here it feels a little bit like two different, slightly two flavors of more or less the same architecture. And this again, they are like historic architecture people tried, but by now they are not that common in the literature. Another thing is that the Elman networks, they are, let's say, like the predecessor of the RNNs. So in fact, the RNNs are just like an evolution or a simplification of the Elman networks. So yeah, so we're saying that one of the challenges, so also why people are not using RNNs for all possible type of problems with sequences, and why even to this date people are trying to use CNNs for them, is on so the training problem, in that we say one of our motivations, we have two motivations for using sequential data. The first one was we want to have fixed input for non-fixed data, but also we want that this non-fixed data is grown over time. We consider the historic information. And here it comes like the very first problem that we have with RNNs, and it's this idea of vanishing exploding gradients, in that what happens is, and we can see it, so here in the visualization that simplifies it. So given that we are using this recurrency and from the previous states, what basically happens for this input, so this blue one, is that the impact that this blue input has on the first hidden layer, on the first state of the hidden layer, is, let's say, very high. But as we do this recurrency over time for the multiple inputs, then this starts to fade. So when we get to the last one to generate our output, really the influence, the effect that the first input is having on the last hidden state for our output is minimal. So it vanishes, it appears over time. And this means that on one side, this will not be influencing our result, but also this is a problem in software hour activation, in that this starts to become so small that in the end it has, so it's not having any impact, right? So this is basically the first thing. Then the opposite will be the exploding one, in that very fast the gradient can grow in value to the point that is no longer representing really anything. So for both of them, there are solutions. Of course, solutions are not perfect because it's still a problem in the literature, and even to this date, you see publications that try to address them somehow. But these are things that we have to have in mind. The other challenge with the RNNs is that they can get stuck into saddle points. So as we are having some more parameters, of course, then they can have they cannot have saddle points, and that's why here we try to solve it with different training techniques. And there are, for these three problems, vanishing, exploding, and gradients and saddle points, we solve them primarily with heuristics. So there are rules of thumb that we might be seeing into how to solve them. But in general, these are things that we have to have in mind. And this is basically, even though RNNs might be so intuitive for sequential data, this topic of the vanishing gradient makes them less interesting, to the point that so CNNs or of course transformers and so on have become good alternatives for RNNs. Then, although these days we call it like RNN to basically mention all the family of models, there are of course not only the RNNs, let's say like these ones that we saw, let's say like this one here. This is like the Ellman RNN, pretty much. But there is, of course, other ones, there are other flavors. And you might have heard, of course, of the Lstm. The Lstm is like the next step for the RNN. And here the idea is that we'll have the memory cell to forget. And this is relevant. So for, again, like the topic of we have long sequences, and we want to basically handle some way where for example, if a given input, so if we have this problem of vanishing gradient, and we want basically to flush it somehow, then how can we do it? Well, the idea for the LSTM is that we integrate this forget gate. And let me here try to modify it. So here we see that we're having, here for our sigmoid, and if we see here, and we compare the memory cell and the forget gate, so here what is happening is that on one side, here we're adding, so before the recurrency happens, we're adding here this forget gate that defines if we should consider some information or not. So not only we're having this memory cell that let us store additional information, so here, but also we're including a way to release this information. So, but we're seeing that in fact, let's say like these points are basically the same as the RNN. So the only thing that we're adding is we're adding new things. So here we're adding this memory cell as additional information. And then in this part, we're adding the forget one. So we can see here that there are basically improvements. And if we look at the different elements of the different states, so different gates, so the forget gate and the internal state and so on, we see that in fact they are just aggregations. So from the different input gates and input node. So here what we can see is that it might look, let's say from looking at this diagram, it might look, let's say, like a bit overwhelming, or you might be thinking, oh, there is so much is happening, but in fact, not really in that. The Lstm is just this aggregation from the different internal states and a forget gate. And then the value how we compute is just this output gate combined here with this forget gate. Yeah. So, and then if we see how it looks unfolded, then we look at how we have, again, the same as an RNN for each input, we'll be having, so here, our hidden state, and this will be shared across time. Yeah. And if we look so here for the forward pass is, again, we see that compared to the RNN1, there is actually no difference. And also if you see the different, so the output gate and different internal state and input and so on, in fact, we are just having the same, so we're here passing the input with the matrix of weights for a given point and the hidden state and the sigmoid. And we're seeing that, in fact, this is basically the same. The only difference is that we're storing different weights of matrices. So here, again, the only thing that is helpful is to have, let's say, like redundancy, to have additional information. But otherwise, let's say from the implementation and from the logic that we're having, we're not really adding anything new, really conceptual, because we're not saying, okay, we'll be doing this completely different, but no, we're just adding more of the same, so to say. So then this matrix of weights can capture different aspects, and as a result, we can have a richer prediction. Because again, this comes to the second point that we discussed on what drives the whole research in so sequence data, and is we want to have rich representations that consider sequences of so long lengths, yes. And by adding these additional terms, we are enhancing this richness, because now we're making what was an RNN that was relatively simple in that we only have the recurrency of this summation of the matrix of weights with our output and the previous hidden states. Now we're adding more of that. Yeah, so as a result, we should be able to model so richer, obtain richer representations as a result, ideally reach better outputs. And then another idea that people have as architecture, in fact, is pretty much a training trick by now, or just a way how you can improve your results. But in the beginning, it was seen as, let's say, like a separate architecture, is this idea of a bidirectional RNN, in that, so we always think that we have to train, let's say, from point, let me modify this. So normally we think about the sequence as that we start on the first point in time, and then we advance across time, right? So we start first step, second step, and so on. So on a growing order in time. And this would be like this part here. But the idea of the bidirectional is why not do it reversely, and then start with the last value and go all the way to the first one. And then we will combine these two hidden states for the output. And this is basically something that is always, it's like a good idea to try for any type of forecasting task. And if you look at, for example, a modern architecture for doing time series forecasting, such as NBITS, this is pretty much what they do, in that they work first incrementally with the sequence, and then they go in reverse, right? So, and of course, they do not use an RNN. It's different, but they take this idea of going forward and going backward. And we see that here how the architecture is done is that in reality is basically the same. I mean, it's in the end just an RNN. So just the only difference is that we're having these two hidden states, one when we're going incrementally and one when we're going decrementally, and we're just aggregating them. Otherwise, it's the same. This you may be thinking, oh, but why people do that, and it sounds like a little bit unintuitive, but in fact, it actually works. So whenever you're having a forecasting task, it makes sense to do this decrementally. And then if we think finally about applications, so for all these architecture we saw is, well, we know them, right? So we can use them for all type of text tasks and image captioning, but also time series forecasting, event sequences, and so on. So this is basically the first survey that we have reviewed, and we'll be going to the second one. Are there any questions? Otherwise, I would suggest we do a break of 10 minutes, and then we go to the second point that we'll be reviewing. I see no questions. So, okay, then I will stop sharing the screen. Stop share. And let us have, now is 11:14. So let's come back at 11:24 for our second publication I will be reviewing on relevant aspects of RNNs. So we're back. Let us go to our second discussion in that this is also a very interesting publication called an empirical exploration of recurrent neural network architectures. And it's interesting because so far we have discussed, okay, we have RNNs and we have LSTMs. And we saw that although they're not the only ones that exist in literature, and there are many others, they are definitely so the most popular. However, something that here in this case, Josefovics so was reflecting is that it's rather unclear why we are using LSTMs in that LSTMs are more complicated than RNNs. And these additional parameters, and if we go back to our to the first publication that we discussed, so these so memory cell and forget cell that we're having, they are by now, let's say, like established and they're accepted, but it's unclear. So why it's supposed to be better? And not only that, but also if we really need those components. And the objective is, or the objective that this publication had was to say, is it really the optimal configuration for an LSTM, or is it possible to explore other architectures within the LSTM and identify if there can be some modifications to them? And indeed, so if we look at, so what they found is that it is possible to just add a bias of 1 to the forget gate to close the gap between LSTM and the GRU. The GRU we have not seen so far, but for those who do not know, it is let's like a simplified version of the LSTM. And yes, so if we start about what motivates them is we say, okay, we have the RNNs, and RNNs are good because we have these different hidden states that are recurring. The downside is that, as we saw, is we have this vanishing gradient problem or exploding, because as the sequence starts to grow, then it becomes harder to train. And people then said, okay, let us add this forget gate and this memory 1 in order to handle. So the memory 1 is for rather the vanishing gradient, and the forget 1 will be like exploding gradient. But still, nobody really provide any way to justify why we need these additional components. So the findings that so here Josefovics had was that we can get better results in LSTM by doing two things. One is adding this bias of 1 to the forget gate, and the second one was to using dropout. And let's say dropout by now is more or less a very accepted and standard technique that pretty much everyone adds it no matter what one is doing, because it just works. But that when the publication came out, and this publication is also a bit historic in that this publication is from 2015 also. So as a result, back then, not everything was as well understood as it is today. So they realized, okay, we have to add back dropout, I mean, and also this bias. But not only that, but also realize that in fact, not all these elements that the LSTM is adding are actually relevant. They basically claim that the input gate is important. This output gate is unimportant, and the forget gate is very important for all problems with exception of language modeling. So they basically start by so presenting how an LSTM looks like. This looks a bit a bit different than the example that we just saw in the previous publication, but here I just put on the right side what will be the equivalent for different, so here, elements of the LSTM. And in fact, we're seeing that they just use a slightly different notation, but in fact, we're just talking about the same thing of we're having just our matrix of weights for an input and the previous states, and then we're passing them through this activation function, in this case, RC modes or hypertangent. And then in the end, we just compute, so for a given input, what will be the current hidden state. And we have, given that we have this sequential nature, we have these two things, the exploding gradient and the vanishing gradient, right? So, and they say this is basically because of the iterative nature of the architecture, and this is part of the nature of this architecture. So it's basically impossible not to have them. However, it is possible to deal with them. And for the exploding gradient, the most common way to do this is there is this very technique called gradient clipping that is just the basic idea. It is will define a threshold for the gradient, so how large is allowed to grow, and then if it exceeds that norm, then we'll ignore it and take the highest value that we have defined. So this is something that is very straightforward, and actually it works. So it's something that is not perfect, but it works. Whereas the vanishing gradient is there more challenge. Yeah. So here this is something that we cannot so just define, let's say, like a minimum value for it, and you just use it. And therefore, that means that we can see here that the RNNs, we can use it for short sequences, but no longer ones. And this is a problem because we're saying what we want in doing research for sequence data is we want to handle long sequences. So what is the option here? And then we're saying, okay, the Lstm might be an option for this. And here, so what basically we say is that the Lstm is nothing else than RNN, but this handle this vanishing gradient problem that is harder than the gradient clipping one, where we saw a solution by doing a reparameterization of the RNN. However, even though it's trying to solve the vanishing gradient, it does not have a representational advantage because it cannot solve completely, or it cannot really solve fully this topic of the vanishing gradient. And this is basically because they explain it with the hidden state, in that in the Lstm, what is happening is that we're basically computing this delta, this difference between STs, between the hidden state of a previous state and the current state. In the RNN, we basically are computing it with a matrix vector product, and then we have the activation function. Whereas here we're having this difference in the work computing, and this is where they conclude that it's not possible with the Lstm to, in the end, handle the problem of the vanishing gradient, because given that we're computing this gradient, we cannot, in the end, we'll always have this vanishing gradient problem. So that means that even though the Lstm might look more complex and might have, let's say, more things included, in fact, it is neither better nor worse than the RNN. And this, again, brings us to the one recurring topic that we will be seeing across the course, but also when you'll be looking at the literature, is that very often we see these very advanced architectures that appear in the literature, and then someone comes and say, hey, but actually, with just a very basic RNN where we do this slight modification, we get the same results, or we do not observe any difference with regards to these more advanced ones. So here, basically, Josefo observes, out of the box, the Lstm is neither better nor worse. Yeah. And then, well, so here they define the elements of the Lstm. That is basically what we just saw in the previous publication. And the only difference is that here they, instead of using sigmoid as an activation function everywhere, they work with so hypertangent. But otherwise, we can see that we have the same elements, right? And then here we have two hidden states. So the CT was basically this one for the forget gate, so that it allows. So we're using this to try to fight our vanishing gradient, and then we have, of course, the final one. That is the one that we'll be calculating. Will be like our output. So here, so far, so good. And here again, what I want to emphasize, and we'll be having a seminar where we'll be building an RNN from scratch, because let's say, like at first glance, it might seem complicated, but in fact, and as we're seeing from these operations, it is something very basic, where it is just yeah, so a product of inputs and here a weight of matrices, and then we have some non-linearities, and we're just basically aggregating these, and this is pretty much what we're doing in our architecture. So in fact, it's a very straightforward approach, even though on paper it might look a bit more overwhelming. And then just was basically saying that how can not only we have this challenge of these models are so it's unexplained why we're adding them, but also the other thing that is not explained is how do we initialize them, and in this case, so is how can we initialize the forget bias for the Lstm. And so just before it goes into the literature and says, okay, what most people do is they are just initialize them with small random weights, and this is basically what we normally do, right? So we just take as if the initial state a very small random weight, and what I notice is that indeed it works for many problems. It's fine. This basically means that we are setting the forget gate at 0.5. But here again, by using these small random weights, this can so basically trigger the vanishing gradient problem. So this might be a problem with so long-term dependencies. So basically what it suggests is that we should initialize the forget gates with larger values. So not go with the small ones with 0.5, but rather between 1 or 2. Yeah, so this should enable that we have this gradient flow and we do not observe the vanishing gradient right in the beginning. And the one problem that I notice is that if we are not able to properly initialize the forget gate, what might happen is that we'll not be able to so basically handle long-term dependencies. And they present so the GRU, that is the recurrent unit, that basically the GRU is like a simplified version of the Lstm. The idea is that so here we are having pretty much the same version as the Lstm, but we're seeing that here if we compare so our Lstm and the GRU, we see that they're not striking differences, but the GRU provides a simpler representation. And still, for most tasks, the GRU normally outperforms the Lstm. So, and therefore, so here, what was the motivation of Scott was to say, okay, what can we do? How can we change the Lstm in order to obtain results that are comparable to GRU architecture? And then, so they went and did an architecture search. So they look at, so what up to 2015 was like the hundreds of best architectures for Lstms. And then based on this, they did a architecture search where they modified these 100 architectures. So they came up with 10,000 different architectures. And then for each of them, they had like the hyperparameters. So in total, they were basically dealing with 230,000 hyperparameters. And they had multiple tasks for working with these architectures. So they had one where they were trying to compute digits of two different numbers. Then we're doing some modeling of XML, so it's markup language from synthetic data sets. And then they were doing a language modeling task. And then they came up with what would be like the best architectures. And then these are basically four ones. The GRU that came on top, and then modifications of the Lstm. And you can see that, so if we look at the different modifications of the Lstm, then primarily what is happening is so that we are adding additional inputs with the different weight metrics. For example, we can see it here in MUT1 versus MUT2, where here we remove the hidden state with the weight metrics that we have here. but otherwise this remains here the same. And but otherwise, these basically just slight modifications that actually they resemble. If we look at how this how our GRU looks, they resemble closely how the GRU is actually. So here, basically comes down to, okay, so why are we doing these architectures if we can just go and grab the GRU? And this is probably like one of like the main takeaways from this work. And also, if you look at the common understanding for working with sequence and data and so on, is that often people say, so let's say like in the intuition of people, so it will be that RNNs is the first baseline that I try. Then if I want better results, then I will try an Lstm, but I not necessarily might use it because Lstm is more complicated. So it's a bit, it's also computationally heavier, but I expect I will get better results. And then if I want still to improve it, then I will try the GRU. But here we're seeing so multiple things. One is, so here Joseph is saying there are no differences between the Lstm and the RNN, unless we do these modifications that we said, where we'll be changing a little bit the bias and we'll be adding dropout. But out of the box, the Lstm will not represent so our sequences better than the RNN. And then we have the GRU that outperforms the Lstm in all tasks that they compared, unless we modify the Lstm to something that resembles the GRU, right? So that means that for us, whenever we're trying to work with so establish baselines for our sequence problems, then obviously the first thing is we set up an RNN. That's the very first step. But then if we're thinking about what comes next, then from what just Fabric is presenting, we should try a GRU and not an Lstm, right? Which is actually a bit unintuitive, because if we look at the literature and also we probably look at how many publications they consider Lstm as a benchmark, and they do not include GRU, there are likely many more than those that consider GRU and do not consider Lstm. So yes, so this is for this publication. Are there any questions or anything that you would like to discuss? No? Well, that's great. I hope that means that everyone is understanding everything so amazingly. So then we'll have a third final one. And then I suggest that we have also another break. So now it's 11:42. So our third one will be at 11:52. Yeah. So the third block, I will mark it here in the chat window. 11:52. So I'll stop sharing and then let's meet again in 10 minutes. So now we are back to our third block. This publication is more recent than the two ones that we saw before. So this was from 2019 compared to the previous two that were from 2015. But it has an interesting idea that also it is connected to one of the things that we have been exploring. So it has, I would say, two things that are relevant for us. The first one is on, and we saw it a little bit in the previous work, where we're saying actually LSTMs are not as good as people will tend us to make us to believe. And in fact, a RNN is as good or as bad as an LSTM, and a GRU is better. And this publication has a similar idea in showing how more complicated does not mean that it is better. And it goes to show that using a single RNN, we can have similar results or probably even better than more complicated architectures where we have stacked multiple hidden layers. This is one point. And the second main takeaway, and it is connected also to, for example, to transformers, is that it also shows how, in fact, order in a sequence is not that important to get good results. So we keep saying one of the motivations of why we're using all these recurrent architectures and why recurrency is crucial for sequences is because we have all these ordered data that has this sequence, and we need it in order to make predictions. We cannot just so break it, and that is what it makes these type of architectures essential, and we cannot use CNNs or something else. And in fact, here, so here they show that it's possible to not completely break with the order, but do modifications to it so that we can make simpler architectures and not have these more complicated architectures. And this idea of playing with the order of the sequence, we will be also looking at when we'll be on Friday discussing about CNNs for sequences, where also there are ideas of saying, let us try to look into techniques into how we can handle long sequences for the CNN. So if we go back here to this one of Turek, so how do they start, or how can we summarize it? Is that they show how a single layer in an RNN can basically do the same as one architecture that has a deep stack of hidden layers. And this basically because in the end, what we need to consider is not looking to how many layers we are putting into the architecture, because adding layers, it means, of course, dealing with hyperparameters. We also need to handle the weight matrix and so on. But rather consider a causality. A causality basically is this idea of the order of the sequence, that we need to first consider the first step, and then the second step, and third step, and so on. So point one, T1, T2, T3, and so on. And they say, actually, this is not that important, because also we can look at the bidirectional network that we discussed just a few minutes ago. So if we go back to here, this work here, and in the bidirectional RNN, in fact, we also have this idea of a causality, meaning that we are considering, we're going backwards. And this shows us that it cannot be that the xt has some dependency on xt plus 1, because we can go in reverse. And this is basically, so what they're saying is that if we make use of this causality, we can basically so skip or not make use of these more complicated architectures. Yeah? So then the motivation is that, as we were seeing with our previous publication with Josephovics, there are so many architectures that are for LSTMs, RNNs, and so on, and so many different flavors and so on. So it is very complicated to find how we can find the right one for our problem. So not only there are so many literature, but also we start to evaluate them. Well, this takes a lot of time and resources. So this is unfeasible. And what they notice is that the RNNs are in their causal architecture, meaning that so we are making use of the fact that one input is dependent from the previous one. But then they also see that bidirectional RNNs, they do not make use of that, given that they're processing the sequence forward and backward. And these bidirectional RNNs actually they get good results. So here the idea that they have is why not they try to simplify this architecture exploration. And their objective is to show that this single layer RNN can have basically the same results as any stacked RNN, but then we'll be having the constraints on these recurring weights and the outputs. So that way we can learn the solutions in a single layer. And for this, I propose something called the delayed recurrent neural network, or DRNN. Yeah, so and the idea here is that we want to have depth without having additional layers. So this is like the crucial thing. But then for this, we'll be introducing a causality to the RNN. So that means we cannot longer anymore make use of this fact that we'll be having order in the sequence, and that we'll consider for each step, we're having for each input a given hidden state, right? And so if we again refresh how an RNN looks like, and by now we should be very well familiar with, we have basically our hidden state, so this H hat, that it just consists of this matrix of weights and for a given input, and so a matrix of weights for the previous hidden state and a bias term. And then our bias is, not our bias, I mean, our output is a result of basically here an activation function. So for example, so the hypertangent from these hidden states and the bias, right? So far so good. We have already seen this many times. And normally what we do is that we don't just stay with one single here state, one single layer, but normally we are stacking them, right? So we try to have many recurrent units to have this depth, because we believe that this way we'll be able to capture these longer patterns in the sequence, and also that way we can make use of the full sequence and so on and so forth. So this is, let's say, something that is gospel in the RNN literature, and we always use it for an RNN architecture. So we see that basically this parameterization is basically the same thing as an RNN. We just have different weights for each layer at any given step, and also the same thing will apply for the hidden state. So in the end, the stacked RNN, and with stacked RNN, we can basically denote pretty much all RNNs that we use in practice, because we don't really work with a single layer RNN. We end up having these multiple, so these k layers of hidden state vectors. And so if we think about how we can so try to address this in not having to deal with this stacking, it is that we can have, for example, incorporate nonlinearities at some point, right? So we can have, okay, let's have some activation functions in between the different hidden states, and that way we can, for example, avoid this problem with the not having to have that complex architectures. But adding these nonlinearities, well, it will make our solution more computationally expensive, and also in the end, it just makes it so less transparent, right? So what they said, okay, is let's look at let's try to make use of this causality, right, with this idea of the delayed sequence. And here, let me show. So basically, so what they're proposing is something that is very basic as a trick, and the idea is let us have some delay, meaning let us skip here our inputs before getting a specific output. So in this case, they have this delay that is 2. And this is basically, if we think about that, so now we're not respecting anymore the order. We're not saying, so for each of our, so here, inputs will be having a given hidden state with a given output and so on. But rather here we're saying, okay, we'll be jumping in between. So that way, of course, we are saving, we're not needing to have all these so layers for each individual input, but rather we can just simplify it. We can have this delay. The other thing that here we'll be seeing is that, and this is something we'll discuss on Friday, is there is this concept of dilated convolutions. Now this is basically the idea of how we can use CNNs for sequential data. And dilated convolutions is very close to basically the delay in the RNN, in basically, so considering points that are not one, that are not one after the other. And if we also think further, basically something similar happens in transformers, where in the transformers architecture, we are not handling the sequence in a hierarchical sequential order, but rather we are basically just doing like a search among the elements in sequence and taking those that are the most relevant for our model. And therefore, that means that we'll be skipping also as well. We're having to say delays, or we'll be basically skipping some elements in sequence. So here we see that they're basically just proposing, so say like a trick, but this has further consequences because as we see, we can see that the idea of requiring order for our architecture, this is not necessary, and transformers basically prove that this is not the case. And the other thing that they show is also how this idea of more complex models, they are more relevant. It's also not the case. So what does it mean for us for our research and for the projects and so on that we're working with? Well, the main takeaways that we can have so from these 3 publications is 1, always try a basic RNN as a baseline. 2, do not believe that more complex architectures might get better results, so be skeptical about them. And 3, there are very basic tricks that we can have that let us have very similar performance to top architectures. We have seen how we can take, for example, the GRU, which is like a simplified version of the Lstm, or we can do modification of the Lstm to make it like a GRU. Or in this case, we can see how by having these delays, we can handle so sequences without having this stacking in the layers. So yeah, that's everything for today. Are there any questions? I will be, of course, putting the links, we'll be putting on Canvas, so you can, of course, read these more in calm, and also if you have other questions and so on, we can discuss them. Otherwise, if there are no questions, that will be everything for today. So I do not see any questions, then yeah, then that will be everything. And then we'll continue on Friday, where we'll be looking into CNNs and how we can use CNNs, because that will be the other thing that will be important to learn on Friday, is that CNNs can have as good or better results as RNNs and LSTMs and so on, but they are computationally faster. So this will be also something that you might be interested in considering for your research and projects. All right, well, then thank you everyone for your time, and then let's meet again on Friday.